we're now going to look at the geometric series, which is just the sum of a geometric sequence. Again, this is something that you need to learn by heart. I'm afraid no nice picture to go with it this time. So how do we write down the sum of the first n terms for a geometric series? Well, that's going to be a plus a times r plus a times r squared plus, and so on, until I get to the last term in my series, which is going to be ar to the power of n minus 1. Now my trick this time is to multiply the whole thing by the common ratio, which is r, so r lots of Sn. And I do the same on the right hand side. I multiply everything through by r. A times r would give me ar. Ar times r would give me ar squared. Ar squared times r gives me ar cubed. And I work this on all the way through the line until I end up with ar to the n minus 1 times r, which would give me ar to the power of n. Now I take one equation away from the other. So the sum to n minus r lots of that sum to n is, well, I've still got a, but I'm going to subtract the ARs, I'm going to subtract the AR squares, the AR cubes, and so on all the way down, and the last thing that I'm left with that hasn't got a partner is AR to the n. Factorising the left hand side is Sn lots of 1 minus r. Factorising the right hand side is a lots of 1 minus r to the n. Now I can divide through to give me that the sum to n is going to be a lots of 1 minus r to the power of n all over 1 minus r. This again is something that you need to know and memorise. Obviously r can't be equal to 1, because if it was, it would make the denominator of this 0 and I'd be trying to divide by 0. Incidentally, if r was 1, if the common ratio was 1, if my sequence was beginning with a and the common ratio was 1, then the first term would be a, the second term would be a, the third term would be a, and so on and so on and so on. And I've just got the same number n times over. And we have obviously a much nicer way of finding the sum of that series. Let's look then at how we use this. So here I have a geometric series, and I can see here that the common ratio r is going to be minus a half, and even more clearly than that, the first term in this is 4096. I don't know at the moment how many terms there are in this series, so that's going to be something that I need to work out first of all. Now to do that, I know that the last term is 1, so I know that 4096 times by minus a half to the power of n minus 1 is going to be equal to 1. Or that minus a half to the power of n minus 1 is equal to 1 over 4096. Now, I know already that n minus 1 must be an even number. Why? Because I know that this side is positive, and I need to multiply a negative by itself an even number of times to be able to generate that. I'm now going to drop the negative for that reason, and actually for a different reason, in that I want to use logarithms to solve this problem. And I want to use logarithms because the unknown is trapped in the indice. So I'm going to take here logs in base 2 of a half to the power of n minus 1 is logs in base 2 of 4096. Now using logarithm laws, that's going to be n minus 1 lots of logs in base 2 of a half is logs in base 2 of 1 over 4096. Now another logarithm law that I know is that if I've got 1 over 2, then that's the same as minus logs in base 2 of the denominator, and I'll apply that to the right hand side as well to say that that's the same as minus logs in base 2 of 4096. Now logs in base 2 of 2 is just 1, so this becomes n minus 1 times by minus 1 is equal to minus logs in base 2 of 4096. Dividing through by minus 1 and throwing that onto my calculator, I find out that n minus 1 is 12, which is a good thing because we knew that that was going to be an even number. Adding 1 to that, I've got now that n is 13. Seems a long way ago since we started this question. I actually want to find the sum of this series, so I'm now going to use my formula. So I want the sum of the first 13 terms, which is going to be a times 1 minus r to the power of 13 all over 1 minus r. Now in this case, a was 4096 and r was minus a half, so that's going to be minus a half to the power of 13 all over, where are we at now? 1 minus a half. Now clearly at this point we're just going to resort to a calculator, and throwing that all onto our calculator we end up with 2,731. Finally, we're going to look for the least number of terms required for this geometric series to exceed 3 million. So again, similar to questions that we've looked at before, we're just trying to find a different way to phrase these so that we look at every possible combination of unknowns. We can see quite clearly from the start of this question that the first term is 2. We can see that the common ratio is going to be 3. And what am I doing here? I'm wanting to find out when does Sn exceed 3 million. Okay, so that's what the question's asking me for. I also know that Sn is going to be A, which is 2, lots of 1 minus 3 to the power of n, all over 1 minus 3. Well, again, we're going to solve this as an equality, and then we're going to look at putting the inequality back in at the end. So what I want to solve here is that 2 lots of 1 minus 3 to the n divided by, now 1 minus 3 is minus 2, we want to know when that is equal to 3 million. Now simplifying this, that's going to be minus 1 lots of 1 minus 3 to the n is equal to 3 million. And expanding that is going to give me 3 to the n minus 1 is equal to 3 million. Or rather, 3 to the n is equal to 3,000,001. Again, the unknown here is the indice, so I'm going to use logarithms to solve this. So I'm going to take logs in base 3 of 3 to the power of n is logs in base 3 of 3,000,001. This is going to give me on the left hand side n, and I can throw that into my calculator and it tells me that my answer here is 13.5 something or other. Well, that's when it's going to be equal to 3 million. I want to know that when it first exceeds 3 million, so n is going to need to take that larger value, so n will need to be 14 for that to be the case.